In this project, I built a mobile robot for SLAM, that is simultaneous localization and mapping. And the chassis of the robot, I designed it with SolidWorks, then had it 3D printed. Over there, you can see the model on SolidWorks. I have holes for the standoffs, for the motors, that's for the motor plates, for the motor driver, for the battery pack, for the Arduino Mega, also for the Jetson Nano, NVIDIA Jetson Nano, for the LiDAR as well, for the camera in case I considered using a camera, but I didn't use the camera eventually. I also have holes for the wires, jumper wires, and all that, and I also have a hole for the holes for the buck converter to place on the chassis, and as well as for the castors. And on the bottom, the lowest chassis, the lowest level at the last level, I had the DC motors there, as well as the motor driver and the battery pack. It takes 186050 battery, four of them, and as well as the buck converter to step down the voltage from the battery pack to 12 volts standard voltage for the motor driver. And then that's what the buck converter does. The DC motor is a 12 volt 280 rpm gear DC motor with wheel encoders. Then on the second level, that's where I have the Arduino. Originally, I intended to use an Arduino Mega, but my Arduino Mega got damaged in the course of building, so I had to switch to an Uno. Luckily, the code was able to fit within the Uno, just barely. I also have the power bank on the second level there. Then on the third level, that's where I placed the NVIDIA Jetson Nano. I used the 2 GB version to save cost, and that's also where I placed the IMU. I used an MPU 6050 IMU. Then on the last level, that's where I placed the LiDAR. I used the Slamtech RP LiDAR A1, that's 360 degree. It has a 12-meter range, and it has a scanning frequency of up to 10 Hz. And then after I finished the assembly, I did some tests so to determine the upper and lower limits for the motor speeds, and that helps me in programming the low level control for the motors. And then let me talk about the code. I had different Rust nodes that I wrote with Python for handling different parts of the SLAM process. I had a node for building the map. I call that the build map node or something, and it used the LiDAR data to update an occupancy grid map. Then for localization of state estimation, I used the extended Kalman filter. I fused sensor data from the IMU and the wheel encoder and the LiDAR. It was kind of a challenge to set up this state estimation part, but I kind of got through it. It may still need a few tweaks or updates, but for now it's working fairly well. So for the SLAM process, that's what I did. First of all, the robot initially assumes that its starting point is 0, 0, 0, that is x0, y0, theta 0, and then it determines a goal location somewhere within its immediate map, and then it moves to that goal location while updating the map. And then after it gets to that goal, it gets a new goal, plans to that new goal, goes to that new point, and then it keeps repeating that until whoever is building the map is satisfied with the level of detail on the map or the size of the map. The map has a fixed size, 10 meter by 10 meter, and then the grid spaces is about 4 cm by 4 cm. Yeah, so that was that. So yeah, so let's see a demo of the SLAM process. I took this video in my room. My room is kind of small and it's kind of cluttered, so I couldn't really do a lot of go through a lot of waypoints, so I just did one from the start point to one goal point.